Alright, now we're going to move to presentation, and I guess this is the most interesting part. So in today's presentation, we'll cover the following points: how to create Typhoon HIL model of the AIT SGC 3-level PV inverter by selecting nominal power and type of grid, how to load these models and settings, then we'll demonstrate how to operate inverter by setting inverter parameters, how to change operation mode, control mode that I was talking about a moment ago, then just demonstration of inverter in action, MPPT mode, DC voltage mode, grid support features, LVRT, and finally our user interface, and we'll show you how easy it is to make your own custom interface. So I will move to this. So in order to actually run our converter, this is the starting point. Okay, this is a simple wrapper, Python wrapper, and what does it do? It actually enables us to select power rating. For this demonstration, I have 4 options. So these are typical ratings of commercially available solar inverters. These are falling into so-called commercial solar applications category, while 630 and 1.2 MV or MVA are more for utility scale applications. So let's select 54.5 kilowatt and 2 grid options, let's say ISC grids and US grid. And this model can be compiled or replaced. We'll choose option compile, and by clicking compile option, we are invoking a PowerShell, which is at first showing our selected options, and now it starts computing of the model, creating schematic and setting up inverter and doing all of that. So as you see, the model is successfully generated. So we'll close this, close, and change the screen. All right. Now I will open the model that is being generated. Invoke settings that are being generated for this power level and the grid. So you can see in section of output settings that settings are already preset, and this is all done based on the power rating. Right, then we'll this will take a few moments, so please be patient. So what I'm doing, I'm opening custom UI and so-called HIL SCADA. HIL SCADA is our user interface, and this is an interface which enables control of our converter. So all of these files are being generated by the previous script. On the left, you see a custom UI. This console is used for controlling the hill. On the right, pardon, I think I made a small mistake here. I should take this one. On the right, you see a console that is used to control our converter. All right. So before we start, I'll show you details on the schematic. So this schematic is generated by script as well. As shown during our presentation, there is a 3-level power stage, PV source, grid source, filter, and this is used for measuring active and reactive power. Right. The rating of converter is also automatically preset, so you can see some values that are corresponding to this 34.5 kilowatt application, or for example, capacitance of the X2 filters, and so on. And now we will start the application. All right, so at the moment we can see that grid voltage is there. Then we start our GUI. Okay, so you can notice that there is some reactive power reading on both sides by reactive power reading from the hill and reactive power reading from our controller. So this is coming from actually filter capacitors. As at this point of time converter is not active, it's actually showing that portion. Now let's change a mode of operation. Let's go to manual mode. So this is a button that you can select the mode of operation, and I'll hit power on. So in about 10 seconds, PV converter should start. As you can see, it is starting up, and it is reaching its power limit, going to almost its power limit. If you increase irradiance, it should go there. Now currently inverter is in MPPT mode. It is rather very simple to see what will happen with the inverter if, say, there is a cloud coming. We have a cloud coming, and we can see that MPPT point shifted down, but MPPT algorithm is trying to correct and go back to its MPPT point. Then let's say cloud is vanishing stuff, so this is actually demonstrating MPPT operation. Let's try to change mode to go from MPPT mode to a voltage mode. You can see in this mode we can control DC voltage manually, and this could be useful, for example, if you want to sweep PV array and see if there are any local maxima and whether we are really operating on the right MPP point. In this case, we know that this is only one maxima, but this is just the reason why this manual mode exists there. Right, let's increase the irradiance to 800. Shift to MPPT mode. Next thing to show is so-called PQ diagram. This is to show how useful this tool can be for evaluating performance of PV inverter and compliance to requirements by certain grid regulations. So we'll start with power factor 1 with full power and reactive power 0, and this is the point you can see on a PQ diagram. And let's command reactive power. At the moment there is nothing happening, but this is due to the fact that this control favors active power versus reactive power. But as we start to reduce active power, we can see that converter is changing and producing more and more reactive power. That finally it reaches its limits, so we can change direction from sinking to sourcing reactive power and slowly increase active power. So as you can see, we have a PQ diagram, and this PQ diagram is used to qualify performance of PV inverter. The other important feature of PV inverters is that they can produce reactive power, and how reactive power can affect low voltage grid will be demonstrated in a moment. Say if we command inverter to produce or to provide reactive power that has an influence to voltage, it boosts the voltage from nominal 230 to 240. This of course depends on grid impedance. And then let's say we go to other way around to sink reactive energy, it actually reduces voltage of the grid. So this feature is very important for voltage regulation, and there are grid codes that require PV inverter to support reactive power control. Alright, so at the end I will show you also LVRT, or low voltage ride through. Okay, so we are seeing operation of inverter in steady state operation. On the first scope screen, it's the DC voltage, followed with grid voltage, and then also inductor currents. So let's try to capture to see what is going on during LVRT event. Let's set a trigger to let's reduce the irradiance a little bit. So voltage, DC voltage is going back to 800 volts. I am armed the trigger. Create an event. So this data is being captured and we can now plot the data. So as it's shown on the screen, you can see that we had a voltage dip, in this case symmetrical voltage dip, that in this case the voltage on DC bus went up. And during this period of time, during the LVRT event, PV inverter started producing positive sequence reactive power. As you can see, there is a phase shift there with the goal to actually boost the voltage, as we showed a moment ago, with having reactive power present. It actually helps the grid to go back to where it was, and this way PV inverter is supporting the grid. And the final step in our demo today is to show you how easy it is to use our custom UI. And literally, this custom UI can be made in minutes. So for example, I would like to, I'm having here active power readback and reactive power readback. And let's say we would like to go to read apparent power. So how do we do that? It's very easy. So take a gauge, it's a little bigger. I'll copy some code snippet here. Open and replace this code snippet. And the only thing we need to do here is really just change a command to an inverter. So let's say we want reactive power. And that's about it, nothing else. Now we can give it a name. Power. We can define the units. And that's it. It's supposed to work. So let's command some reactive power. And you can see now that actually reactive power is quadrature of sum square root of P on square and Q square and so on. All right, so that was it for our demo. Now we can go back to our presentation. While you're still fresh with the demo, I would like to show you a few slides. So we demonstrated PQ diagram. This is actually an abstract of requirements, the new code which is coming up on behavior of DER, or in this case PV inverter connected to low voltage grids. And you can see that it is required that this any DER connected to low voltage network produces reactive power within this range. And so pretty much every country, every jurisdiction has its own requirements, but this can be certainly adjusted in the software. Reactive power control. This is also an example. We showed what happens with the grid when reactive power is sourced or synced. There are certain requirements by grid codes to require a certain level of reactive power to be injected. If voltage falls below a certain level or goes above a certain level. And then finally, LVRT. This is a characteristic that has to be fulfilled. And yeah, we showed a dip that was lasting 150 milliseconds, and we can see here that there's a certain requirement in terms of reactive power that needs to be generated, and yeah, so. All right, finally, this is just one use case of our PV inverter, which was demoed by Typhoon HIL. In this segment of the grid, we had our AIT SGC inverter employed, standard off-the-shelf Schneider Electric 3-phase inverter, and end drive active filters. What is important to know, the difference between our solution versus standard solutions is that our solution is customizable. Basically, you just need to change rating and grid and get any custom solar inverter. As for a summary, so once again, our control platform is suitable for a wide range of smart grid application. It features innovative per unit rating concept and easy to use customizable user interface. It is fully compatible with Typhoon HIL 400 and 600 series and offers a broad range of connectivity options. Our product is targeting HIL applications for industry and academia. And if you're interested in more details, you can always contact us on emails provided below. And once again, thank you for your attention. If you would like to talk to us, please visit us at PCAM in Europe. We would be happy to answer all your questions. And now I will pass back to Typhoon HIL, to moderator, for questions and answers.